Hello, am I audible?
Yes.
ओके. यार काय झालं? बाकीचे लोक कुठे आहेत?
करंडे सर सोडतात आता.
अच्छा, ह्याच्या आधी हे होतं काय? प्रोजेक्ट मॅनेजमेंट.
सप्लाय चेन.
हे मग ते प्रोजेक्ट मॅनेजमेंट कोण घेतं?
ते सेम 3 सेम 6 ला इलेक्टिव्ह होतं.
मग तुमचं पीएम लिहिलं ते काय आहे?
ये ना सर
ह्याच्यामध्ये
SCM
time
आहे.
table. नाही, तुमच्या टाइम टेबल मध्ये काहीतरी एक पीएम लिहिलं ना? मला वाटलं
पीई आहे
ते
सर,
प्रोजेक्ट
पाइपिंग
मॅनेजमेंट.
इंजिनिअरिंग.
PE सर, पाइपिंग इंजिनिअरिंग.
हो सॉरी, पीई आहे का ते? माझा समज होता आतापर्यंत ते पीएम आहे, म्हणजे प्रोजेक्ट मॅनेजमेंट सरांचं काय इन्स्टिट्यूट इलेक्टिव्ह किंवा ते जे काही असेल ते. पी म्हणजे काय? पाइपिंग. So that is compulsory to everyone?
Yes, sir.
Yes.
अच्छा, forced elective.
Yes, sir.
Sir, barely an
Yes,
elective,
yes,
sir.
Huh?
Not even elective, sir. We didn't have a choice.
हाँ, तेच ना. Forced elective. I don't know why they call it as elective. जाऊ द्या, चला, let's start. Is the screen visible?
Yes, sir.
So in the last lecture, we had studied about the different sources of heat generation, internal, external, all, both. Okay, so heat released by the occupants and then solar radiations, then the ramming effect, that is the stagnation enthalpy part, and then control devices, and even the frictional air resistance part. So all these will ultimately raise the temperature inside the cabin even up to 50 degrees Celsius. So like Nagpur, Vidarbha. So then that is the main requirement about maintaining this temperature in a somewhat sustainable zone so that a human being can feel the comfort. So now there are different techniques, different methods used for aircraft refrigeration. So let us deal one by one. So this is the very first method, we call it as basic aircraft refrigeration. So you can see over here, is the screen visible properly? Because the photo
Yes, sir.
is
Yes, sir.
photo itself is somewhat blurred. So here the air will come in because of the compression, naturally higher pressure, higher temperature. Some air taken out before compression, some air after compression. This we call it as ram air. This is naturally compressed air, so high pressure, high temperature. This is at low pressure, low temperature. This is at high pressure, high temperature, so there will be a heat exchanger. Okay, so here we start, let's say 0 condition, that is this. Okay, and then up to 2. So 0 to 2 is my compression process. Fine. Then there will be heat exchange. So naturally this 2 temperature, whatever, let's call it at T2, that will reduce because of the heat transfer. It reduces to what? T3. So because of heat transfer, the temperature reduces to this T3. Then after this point, there will be the turbine. It is auxiliary turbine written over here. Okay, now this turbine, after the expansion, naturally pressure reduces, temperature reduces, and it comes to point of 4, which is the lowest temperature. Okay, and then there is a moisture separator if there is anything not to be passed directly to the cabin, exposed to the cabin, then that is getting out from here. And then finally the cool air, cold air will get passed through the cabin. So naturally it will absorb the refrigeration load and comes to E. So this 4 to E is my refrigeration load. So compressor, heat rejection, expansion, evaporator. We can now call this as evaporator. I'm not using this word evaporator deliberately because we already discussed in the last lecture that there is no phase change. So evaporation is not the process. It's basically the sensible heat part, not the latent one. So I can say it resembles to the evaporator. But in evaporator, it is always a latent part. This is a sensible one. So let us call this as a refrigeration load. Simple words. This is how it completes the cycle. Okay, any doubt?
No, sir.
No, sir.
So I'm making use of the naturally available atmospheric air. Okay? Compression. Then like before compression and after compression, there will be heat transfer. No separate working medium is required. Fine. And then after the heat rejection, then the expansion. So lowest possible pressure, lowest possible temperature. And then it gets exposed to the cabin. To absorb the heat, whatever, let's say 45 or 50 degrees Celsius, it will absorb the heat and comes back to the original condition. Why pressure would change? It is same. So 4 to E would be the same cabin pressure. It's only the sensible heat absorption. So temperature increases. Okay, this is how the cycle gets complete. This diagram is a better one. सिर्फ उल्टा दिखाएं. Surrounding air, atmospheric air, okay. Then RAM air. So this is at the normal temperature, normal pressure, atmospheric one. After the compression, this is at high pressure, high temperature, which is made to flow as a heat exchange with this RAM air. This is the compressed part. So there will be heat. This is my ideal compression process, that is isentropic one. Here, this is the practical, non-isentropic. This is reversible, this is irreversible. Correct? And then from this 3 to 4, this is 3 inlet to the 4 outlet, is my heat rejection. And since this is a practical case, there will be certain pressure drop. So P3 is not same as P4. P3 is higher, P4 is lower. So there is a pressure drop in the heat exchanger. Then at 4, there will be the turbine. So again, ideal expansion process, isentropic one. And this is the practical one, realistic. So it reaches to 5 or 5 dash, whatever you call it. Okay, and then it gets exposed to the cabin. So I'm not using any extra working substance for the heat exchanger over here. Same air, before compression, after compression. This is called as the basic refrigeration, basic aircraft refrigeration system. Any doubt to anyone in this?
No, sir.
Okay. Now slight modification. Basic aircraft refrigeration system as it is with evaporative cooling. So compression same, heat rejection same, but instead of stopping at point 3 over here, that means the heat exchanger part. इसके बाद directly turbine था. Now what I do is I make the air to pass through a chamber where certain, let's say, porous structure is there, and inside that is a water field. Very similar to our household, what you call, matka. Correct? So there will be further temperature drop. So instead of stopping at 3, there will be further temperature drop because of evaporative cooling till 0.6. And then the expansion. So this evaporative cooling, mitti ka matka, same principle applied over here. So instead of stopping at 3 and for expansion starting at 3, now my expansion starting at 6. So naturally endpoint 4, a higher temperature. then this T4 is greater than T7, because your expansion here starts at lower value, here it is higher value. Pressure ratio is same, so naturally end point T4 is higher than T7. So instead of the cabin getting exposed at T4, now it is even further lower, T7. So my refrigeration load is increased, and this is how COP increased. Let's say over here starting point 1. Okay, so refrigeration load was T1 and T4. Basically H1 and H4, but since this is air, I can say T1 and T4. With this simple addition, इसमें मेरे को करना क्या है, कुछ नहीं करना, सिर्फ एक मिट्टी का मटका रख देना है. But because of that, my refrigeration process increases from, let's say, T1 same, but not at T4, but at T7. And what is the effect for compressor? Nothing. It remains as it is. So my numerator is increased, denominator as same. COP is increased. Do you get it?
Yes, sir.
So this is how COP is improved. Let's see here. Better diagram. First heat exchanger as it is, before compression ram air, after compression hot air. ये हो गया. इसके बाद evaporative. So instead of expansion starting from T4 for the turbine, now it is some 4A. So this is 4. Further drop to 4A with evaporative cooling only. So without any extra efforts, extra work, if this would have been dealing with some kind of work, then COP naturally I need to calculate. Here what kind of work is there? Nothing. 0. So your total work is only the compressor part. Is there any work associated with this? Nothing. 0. So initial work remains as it is, but the cooling effect increased. Otherwise this expansion would have been started at this point 4, maybe ending somewhere over here 6, and your refrigeration effect is this much only. But now it is increased up to this point. Its start point is same, but end point is shifted towards the left hand side. So as such, increase in the refrigeration effect, compressor work is same, COP is improved. Do you agree? Any doubt?
No, sir.
Now further attempt to increase the COP. So third system is called as bootstrap system. Let's see this. Compressor. This is your ram air. As it is, this is compressed air. Fine. First part is same. So I start from 0, and let's say from 1 ram air, there is a compression. Ideal condition this. Real condition this. Fine. Correct? Isentropic compression and irreversible expansion. Compression. So I reach up to what, let's say this is 2 and this is a 2 dash, ideal one. So I get the same value over here, T2. Okay, let us assume ideal condition. So T2 dash. What I do after this is certain part of the ram air taken out over here. And there is a first heat exchanger. So temperature reduces from 2 dash to 3. The remaining ram air going over here. उसका क्या वो बाद में देखेंगे. So first heat exchanger over here. Let's put it in a simple way, 50% diverted over here, 50% here. So first 50% there will be heat transfer, heat rejection. So T2 dash to 3. Now after this, I will put auxiliary compressor. So further compression process, 3 to 4. So between 3 and 4, there is a compressor. And let's say this is ideal one, this is real one, so 4 dash. And this 4 to 5 is my remaining 50% ram air cooling. Fine. So this 4 to 5 and what I can say 2 to 3. So 2 to 3 is 50%, let's say cooling, 4 to 5 remaining 50% cooling. And then the expander. Now what happens because of this is your expansion ratio increases. And T2 by T1 is P2 by P1 raised to gamma minus 1 over gamma. If your expansion ratio is increased, then your temperature is reduced. Increased temperature is increased. Expansion ratio increased, temperature is reduced. Do you agree?
Yes, sir.
So instead of starting from this particular somewhere here, temperature would have been slightly higher, maybe somewhere here. I started from higher pressure. So expansion ratio is large. T6 will be the least possible temperature in this particular cycle. So naturally, if this temperature is lowered, and if I have to get back to the original condition, so that means your refrigeration effect is increased. Lower the minimum temperature, higher is the refrigeration effect. Let's say your temperature at the start of the compression is 27 degrees, room temperature, fine. If your cooling air temperature is 10 degree, then 10 to 27 is the cooling effect. But if you get the cold air at 5 degree, then 5 to 27 is the cooling effect, which is higher. So here I get a higher cooling effect, no doubt, but at the expense of the extra power. So here there is a compression process first, there is a second compression process. So my work is also increased. Correct. So COP may reduce. So what I have done for that is couple the expander and the auxiliary compressor. So whatever is the expander power output, I make it coupled with the compressor. That means this auxiliary compressor would not require any extra power. That means this compression process is happening free. Are you getting it clear?
So which compression process are you talking about? The
This
second.
one.
So
Are you
how it
able
is
to
free?
see the
Yeah. I am able to see, but how it is free?
coupled same shaft?
Okay, yes. Okay, got it.
So the work done for the refrigeration cycle is only this first part. Second part I need not calculate or consider because that is in support. The anyways expander is doing the or generating the power. So I couple it with the auxiliary compressor. So my input is still the same initial compressor. Second compressor I need not consider. But as the output, the refrigeration effect is increased. I reach to further lower part, T6, because I have a higher expansion ratio. So my refrigeration effect is increased at the expense of the same compressor work. We already discussed we need not consider this compressor work because that is supported with the turbine work generated. So that is like free. So this again enhances the COP. Do you agree? As compared to the basic refrigeration cycle, of course. Here the COP is enhanced. Do you agree?
Sir, can you repeat the part where you were telling that we are able to achieve more refrigeration effect by this auxiliary compressor?
You tell me what you have not understood so that I can explain from that perspective.
Yes, sir. So, what I was saying is that as we are, expanding from a higher higher pressure.
Hmm. Your pressure ratio is
So
higher. So minimum temperature which you can achieve is lower. It is expansion process. So your refrigeration load is increased. You have to come back to the original condition, but from the further lower temperature. Still not able? Hello? Am I audible?
Yes, sir. Yes,
Sir,
sir.
yes, sir, you are audible.
I thought again internet connection gone. That's why. So still able or not? Let's deal with this diagram. You end up over here 3. Okay. And then you start expansion. What temperature you would achieve somewhere here? Okay. Or maybe this pressure line. You end up over here.
Sorry,
Which
sir,
is
I
much
got
higher.
disconnected my internet.
Acha, you got disconnected. I thought I
So,
got
sir,
disconnected.
what I was saying is the curve is
Expansion
going towards.
process, heat
Yes, sir.
rejection is 2 dash to 3. You start expansion from this point where you will end up over here. Correct?
Yes, sir. That is
Or
fine, sir. I was
ah,
asking about 5 to 6, sir.
so
So,
that's what I'm saying. Na? Your pressure ratio is reduced over here. So temperature would be higher. Your pressure ratio is increased. So your temperature is lower.
no, sir. The curve, uh, the the curve will move towards the right as I go down, right?
Go
So,
down. What is down?
I am moving from 5 to 6, basically on the graph.
Huh. Not
So,
right, left. That is what is the
uh,
advantage.
so you have the graph is marked on the right side, right?
No, 3 के लेफ्ट में है भाई ये.
हाँ सर, पर अभी रेफ्रिजरेशन इफेक्ट तो हमें 6 to 1 वाला पार्ट मिलेगा ना सर.
Correct. Which otherwise
तो
would have been somewhere like here. ये 3 है. इधर से
हम्म.
expansion हुआ, reached over here. Can you see the
बट
cursor?
आइडियली, यस सर, आइडियली हम 3 पे थोड़ी रुक जाते, हम पूरा ही हीट एक्सचेंज करते हैं ना सर, जो
क्यों? ये हीट एक्सचेंजर है, यहाँ पे खत्म हो गया.
क्योंकि
You
सर वहां पे
compress
आधा.
it, raise the temperature, and then go for the further heat transfer. Here, what you are bifurcating is only the mass flow rate.
यस सर, सो मास फ्लो रेट हम अभी टेक्निकली कम कर दिया ना सर, तो हीट एक्सचेंज कम
हाँ,
हो गया. तो
हाँ.
अगर मैंने ऑक्सिलरी कंप्रेसर नहीं लगाया होता मैंने,
What
तो
is the driving force for heat transfer? Mass flow rate or temperature difference?
बहुत ना सर, क्योंकि यहाँ पे हम लोग
No.
पावर के टर्म्स में बात कर रहे हैं ना सर.
Huh, so that is mass flow rate is for the sake of taking the time derivative. You take any total mass. Total mass का क्या हो गया? Half हो गया. Is the mass important or the temperature difference? Driving force is what?
टेम्परेचर इज ऑब्वियसली इंपॉर्टेंट सर, बट मास फ्लो रेट भी मल्टीप्लिकेशन में आता ही है ना सर उसके.
हाँ, आने दो ना. कितना मिलेगा उससे? It's a air. How much mass flow rate you can achieve? Double, triple. Instead of that, if I use a simple compressor and increase the temperature, see temperature is increasing directly with gamma, raised to gamma hai. And here you are just like multiplication, double, triple. Increasing the temperature is very easy instead of increasing the mass flow rate. And you are using the same energy, or rather, let's call it in technical sense, power generated by the turbine anyways. वरना वैसे भी वो फ्री वेस्ट जाने वाली थी.
ओके
This is
सर,
not
अंडरस्टूड.
isothermal compression. Isothermal compression होता तो your point is valid. Whether it is mass flow or temperature rise, both are same. This is valid only for isothermal compression because over there, whatever, let's say P2 by P1 is T2 by T1. Fine. Here you are increasing with raised to gamma part, which is more effective. Okay, this is isentropic compression. Isothermal होता तो fine.
Yes, sir. Understood.
जितना प्रेशर का चेंज उतना ही टेम्परेचर का हो जाता. Fine. Not isothermal, sorry, isocoric. Because your volume of the heat exchanger is same. So you increase the mass flow rate, naturally temperature will be what I can say correspondingly change. Ratio would be same. P and T, volume is constant. It is a control volume. Na? Heat exchanger is a control volume. So P1 upon P2 and T1 upon T2. That is okay. But I'm using a compressor and changing the temperature not in a linear sense, but by making the isentropic compression process. So because of that, naturally your temperature is increased. What I can say, the rate of increase of temperature, or the let's say final temperature, in a simple compression process के बजाय isentropic compression process is much higher. So I'm taking that advantage. Over and above, this compression process is like something which I'm getting free, since I am coupling the shaft of the compressor to that of the turbine. So I know that the isentropic compression process would be much effective. That too getting freely executed. So because of that, my lowest temperature 6.6. Here in this chart it is 6 dash. Okay, fine. 6 dash will be much lower. वरना आपका हीट ट्रांसफर जो यहाँ पे है, that is like over. आप ज्यादा से ज्यादा क्या करोगे, पूरा मास फ्लो रेट यहाँ पे डाल दोगे. So this point may shift somewhere over here. I agree. But
Yes,
not up to this part.
Yes, sir.
It will be
Yeah.
somewhere in between these 3 and this, whatever, let's call this as 5 dash. So 3 and 5 dash, इसके बीच में कहीं पे आप रुक जाता है. Effect of mass flow is always lesser than effect of compression process. Isentropic compression, I mean to say. You change the compression process, naturally it will change. Your point is absolutely valid. That is why I am using a compressor and trying to execute an isentropic compression process. Further, I need not do anything extra for this. It is coupled with the expander. Free. तुका म्हणे जाता जाता. So I am reaping the advantage of this free compression process for isentropic compression and increase the pressure differential delta P for the turbine, so that this minimum temperature would be on the lower side. And in that sense, I am saying that it is on the left hand side. आपका point बराबर है. This would have been shifted somewhere over here, but it will never reach to this point.
Yes, sir. समझा.
Fine. Any other doubt to anyone else?
No, sir.
No. Good. I think this diagram is better. Ultimately, same thing. Here you are taking the tram air 50%, let's say here, 50% over here. So here certain cooling and remaining cooling after the compression. So here there is a heat rejection, then the auxiliary compressor, which is coupled with the turbine. So that is like getting freely operated. And then second heat exchanger. More the heat exchange, lower will be the temperature. Basically your 0.6 itself is shifted. And then further your pressure issue is also higher. So 0.7 also shifted. What I can say, more towards the left hand side, 0.6, more towards the left hand side, further lower will be 0.7. Do you agree? 6 को मैं
Yes,
जितना लेफ्ट में लेके जाऊंगा उतना 7 और लेफ्ट में और कम टेम्परेचर में जाएगा. That is
Yes, sir.
what
Yes,
I
sir.
want, because then this entire thing would be my refrigeration effect, which is increased, and this compression process free, no extra efforts. So this is what is called as the bootstrap aircraft refrigeration system. Okay, any doubt?
No, sir.
No doubt. Fourth system is called as the reduced ambient system. Now how this works? Input same, RAM air same, compressed air same. Okay. But instead of having the heat transfer between the RAM air, that means low pressure, low temperature, and compressed air, that means high pressure, high temperature, I expand the RAM air itself. So this low pressure, low temperature goes to even further lower pressure and lower temperature. Okay. That means state 5. So here there is expansion 1 to 5. And this 5 comes in contact with the compressed air. So this is, let's say, lower temperature. This is compressed air, that means higher temperature. So there is further higher amount of heat transfer. And higher amount of heat transfer, that means instead of stopping somewhere over here, it will further go to 0.3. More heat rejection. No? Delta T is higher, so more heat rejection. Higher the delta T, higher is the driving force for the heat transfer. So instead of T1 and T2, T1 and T2 difference. Now this would be T5 and T2. Here this is expanded air. So T5 and T2. Are you getting it?
Yes, sir.
So because of that, the amount of heat rejected, otherwise somewhere might have stopped over here. This is now increased. Total heat rejected is increased. So lower temperature, T3. Okay. And then further part is same turbine. So after 0.3, there will be expansion. It reaches to 0.4. And then there will be the refrigeration effect. But instead of stopping over here, in bracket because of 0.1. 1 पहले क्या था? Lower temperature, low temperature, low pressure. Atmospheric, let us call it atmospheric pressure, atmospheric temperature. P1, T1. But now it is expanded using the auxiliary turbine. So this is lower pressure, lower temperature. The atmospheric pressure, atmospheric temperature. This is lower pressure, lower temperature. So heat exchange happening between state 2 and state 5 instead of earlier case state 2 and state 1. So more the heat exchange, lower will be T3. Do you agree?
Yes, sir.
And lower the T3, lower would be T4. So my refrigeration effect increases, COP increases. Compressor to same hai. Input is same. Numerator is increased, denominator same. COP increased. Fine. And now you are using this turbine power, expansion hai na, turbine hai, and this turbine power together coupled. And you drive anything you want over there. So in this system, I generate power also, I get higher cooling effect also, I get better COP. In the earlier case, bootstrap, there was a compressor coupled with the turbine. So that is why like free power. Whatever power generated by the turbine getting consumed by the compressor, no extra requirement. Here there is no compressor. This is also turbine, this is also turbine. Are you getting it clear?
Yes, sir.
Fine. So I make use of an auxiliary turbine to generate power also, to enhance the cooling effect also, and cumulatively summarize since COP is higher. So here we give the name as reduced ambient because this was the earlier ambient condition. RAM air is almost similar to this. So let's call it a pressure, atmospheric temperature. You reduce it. Reduce by what? Auxiliary temperature, turbine. So this is reduced temperature, reduced pressure. That is why we call it as reduced ambient system. Fine. Any doubt?
No, sir, no.
Okay. The name itself will make the picture clear in your mind. And the last system is a regenerative system. So as the name suggests, there is a regenerative heat exchanger. I hope you are clear with the recuperative and regenerative part. Same 5 heat transfer. Yes or no? Recuperative heat transfer or heat exchanger and regenerative. I hope you are clear.
Yes, sir.
Good, because that is the assumption for this description. So here inlet, then ram air and the compressed air. So there is a first heat exchanger over here. Correct. So this T2, which is higher, now after the heat exchange would be at a lower temperature, T3. Fine. So let us reach from 2 to 3 over here, but we will not stop over here. Instead of passing the same air directly to the turbine, now I am coupling another heat exchanger over here. Okay, so let us start from this T2. There is a heat exchanger, heat is rejected and reached to T3. And now this same air, okay, let's say reduce temperature. And it passes through the turbine, auxiliary turbine, because that is not the main one. So auxiliary turbine, okay. And after this expansion from the turbine, naturally this is the lowest possible temperature. Pressure to hai hi, 4 to 5. This 4 to 5. Lowest pressure, lowest temperature. Fine. What if I make use of certain part of this lowest temperature air to exchange the heat with the incoming one, T3? And that is what is called as the regeneration. Correct? तुका म्हणे जाता जाता. Instead of having the same T3 as the start of the expansion, if I cool this air, instead of T3, if I cool it and bring it to T4, instead of T3, start of expansion, if I bring it further, T4, lower, then naturally lowest temperature is further reduced. वरना ये 3 से start होता, T3, and would have ended up somewhere over here. Let's call 3 dash, say for example, over here, which is on the higher temperature side. And who is cooling this? No extra efforts. The same expanded air after the turbine. Lowest temperature. Why not to make use of it? So certain part goes to the cabin, certain part goes back. But because of this regenerative circuit, the input condition to the turbine is T4, which is much reduced than T3 initial condition, which was here. So first heat exchanger reduces T2 to T3. Regenerative second heat exchanger reduces T3 to T4. So instead of the expansion process starting from this T3, I shift it towards the left hand side further. T4 is lower than T3. So T5 would be the even further lowest possible temperature. And when you shift towards the left hand side, your refrigeration effect 1 to 5 is naturally larger. So this is how COP increases. Compressor को कोई फर्क पड़ा कुछ नहीं. Compressor work is same. What I have tried to always do is to increase the refrigeration effect. in all the cycles, whatever we have studied, compressor work is same. Even though you have used the second compressor, but that is free. So compressor part, that means denominator is always constant. What you increase is the numerator always, and thereby increasing the COP. So here what I made use is anyways freely available lowest temperature air in bracket after the turbine. So instead of diverting entire air to the cabin, let us bifurcate it. Say 70% over here, 30% over here. But because of that, I can reduce temperature T3 as the inlet to the turbine. Instead of that, I will getting T4 as the inlet to the turbine, which is obviously lower. So there is corresponding increase in the refrigeration effect. Are you getting it? Yes or no?
Yes, sir.
Okay, so because of the use of this regenerative circuit, what is regenerative one? जो है उसका ही use करके bring down the properties further. That is what is the regenerative circuit. So this regenerative heat exchanger, I think this you have studied in your gas turbine also, right? Chem 6?
Yes, sir.
Reheat, regenerator and intercooler.
Yes,
तो
sir.
उसमें क्या करते थे regenerator? Same logic, correct? Certain part getting diverted.
Yes, sir.
So we are doing it now for the refrigeration cycle. So this is how we increase the COP. Hopefully no doubt. Any doubt to anyone?
No, sir.
Okay. These are different techniques. Another way, schematic. So 1 to 2, that is the ramming part. 2 to 3 is my actual compression. Instead of 3 to 4, I further make use of the regenerative heat exchanger and bring it down to 5. So instead of 4 to 7 as the what I can say turbine expansion, now my expansion process gets entirely shifted towards further left hand side and I get 5 to 6. So T6 will be much lower than T7, and as such my total refrigeration effect is increased. What are the merits of the aircraft refrigeration? No risk of fire because you're using air. So air is a non-flammable one, correct? Then cheaper, you need not spend money for air, freely available, abundantly available. जितना चाहिए उतना उठा लो. And weight per TR capacity, ton of refrigeration is TR, I hope you remember. So weight per TR capacity is quite low. Correct? Since mass of the air itself is low, so naturally it is lower. Okay. On the other hand, the demerits are the low COP. Who is the culprit? CP value. No phase change. Everything is sensible. So m dot you can play with, temperature accordingly you can play with, CP you cannot change. So CP of air is the main culprit for the lower COP value. You use higher CP value material, means substance, gas, COP will be increased. Instead of 1.005 kilojoule per kg per Kelvin, you use some other gas having higher CP. Naturally, your refrigeration effect will increase. Do you agree?
Yes, sir.
Yes, sir.
And the second point is the weight of the air as a refrigerant. If you want to increase the performance out of m dot, CP and delta T, CP is constant as we have seen just now. So what you have to do, and let's say your turbine compressor also fixed, means the pressure ratio is fixed. So your delta T is also fixed. So if you further want to increase the temperature, performance, then what the only alternative left with you is the mass flow rate. Delta T is also fixed because your pressure ratio is fixed. Then Cp is fixed, it is a material property. So what you have to play with is only m dot. So higher the mass flow rate, higher will be refrigeration effect. So you need to have high mass flow, or basically high weight flow of the air. So that is the demerit. Fine. Any doubt?
No, sir.
Good. So we stop it over here. Second chapter is done. That is your air and aircraft refrigeration system. Now, one point to be discussed is that I have not taken as such any numerical over here, but I can set a numerical in the paper because analysis of compressor and turbine is not something new to you, correct? So I have not shown any numerical over here, bootstrap system and reduced ambient and etc. But I can very easily set it, right? Auxiliary turbine. I will give you the pressure ratio, temperature, khatam. Nothing difficult in that as such. I have covered basic air refrigeration system numerical. Correct? T1 minus T4 divided by, in the denominator it is plus 4 minus 3 plus 2 minus 1. That is what is your COP. That is the basic air refrigeration. Now if you are using it for aircraft application, I can give you inlet condition, compressor ratio, turbine ratio. So that is not something out of the world for you, new to you. So I may set a numerical if I think to do so in your MST or ESC. I have not covered over here because that is a kind of repetition, basically. How to calculate the compressor exit condition, how to calculate the turbine exit condition. It's not a big deal as such for you. Do you agree?
Yes, sir.
So you prepare from that perspective, keep this point in your mind that I may ask. I'm not sure whether I will ask or not. But a simple thing to deal with. Okay, fine. Now how much time left, CR?
Sir, we can start.
How much time left? Let me check mobile.
7 minutes.
Fine. So I will just introduce VCC and then we will stop so that there will be some link for the air refrigeration and the VCC. Is the slide visible?
Yes, sir.
So outline of this very important chapter from your numerical point of view. Vapor compression, then representation on a two-dimensional graphical part, then comparison of the ideal cycle, that is Carnot versus VCC, and then further part why only like single stage, why we can't go to multi-stage, what is the advantage, what is the problem, etc. And the second part is cascade. Multi-stage is like 2 stage, 3 stage, and etc. But using the same refrigerant. And cascade is like 2 stage with different refrigerants. That is the advanced version. So this is how we will cover this particular chapter. Okay, this part we have already seen. The very first chapter itself. So compressor, then condenser coils, then the expansion valve, maybe simple copper capillary like this, or the thermostatic expansion valve, which is also having capillary, of course, or even the solenoid valve, whatever it is. And the evaporator part, which is like the coils which are embedded inside, we cannot see with bare eyes. Then this part also we have done law. thermodynamics M3. Correct. Now I just shift it in the proper schematic. So there is a compressor state 1 inlet condition, that is a superheated vapor, let's say, for example. Okay. Then after the compression, it goes even up on the further side. Correct. So hot gases, hot what I can say vapor, further superheated. Then it will reject the heat over the condenser. It reaches to 0.3. Then there will be the expansion over the throttle valve. Okay, so 3 to 4, there will be expansion. Here we assume that it is, or not assume, we actually control it. So we ensure that it would be at a saturated liquid part. Minimum. It can be even further lower also. That means subcooled liquid also. I hope you recollect these names: saturated liquid, subcooled liquid. SEM3, thermodynamics. Yes or no?
Yes, sir. Yes.
So then this is saturated liquid. So after the expansion, it would be some kind of mixture, liquid plus vapor. Okay, inside the doors. And then this particular two-phase mixture, oh sorry, here, state, let's say 4, okay, passes over the evaporator where it will absorb the heat. And because of absorption of heat, this liquid plus vapor goes entirely into vapor phase. So let's say that it comes back to the original condition. Superheated vapor. So what are the elements of the system? Compressor, then condenser, then the expansion valve, and the evaporator. And whatever we just discussed, let us repeat it. Vapor at a lower pressure and lower temperature. Or let's call it as room pressure, room temperature, whatever. Okay, that is my state 1, inlet to the compressor. After the isentropic compression, it would be higher pressure, higher temperature. That is what is state 2. Correct. Then heat rejection in the condenser. Why pressure would reduce? No reason. We are assuming, of course, ideal conditions, not the pressure drop across the heat exchanger and etc. etc. So we assume that the pressure remains same, and because of the condenser action, temperature further reduces. Okay, it is a heat rejection, so phase change would take place, and it comes to the liquid, saturated liquid. So that is my state 3. And then further, this higher pressure would be reduced. So during the throttling or the expansion, pressure will be reduced. Correct? And because of that, temperature also reduces. Even though it is liquid, after the expansion, it is liquid plus vapor, and you reach to the minimum temperature possible. That is my state 4. And then state 4 to state 1 would be my last evaporator section. So the heat extraction from, let's say, this evaporator section will complete my cycle. So this lowest pressure and lowest temperature change, it remains as it is. Correct? It is just the heat extraction. So pressure remains same. And this temperature, lowest temperature, will absorb the heat and comes back to the original condition. Let's say superheated vapor as shown over here. So this pressure and let's say vapor temperature is as the same as low pressure and vapor temperature. Low means what we have said, atmospheric. So atmospheric pressure and vapor condition. So this state 1 repeats or gets repeated over here, and we say that the cycle is complete. Any doubt in this? We will stop over here.
No, sir.
Okay, fine. So merits बाद में देखेंगे. First of all, the cycle has to be completed. Clear in your mind. Okay, now I stop over here. If you have any doubt, you can ask. Otherwise, we will continue in the next session. And